On April 1st, 2026, humanity left Earth again. 4 astronauts, 1 rocket, 10 days around the moon and back, just like that. Every camera on the planet pointed up. But nobody, and I mean nobody, stopped to ask what 60 years of doing exactly this had already given back down here. Because the greatest conservation tool in human history, the thing that is right now helping save species we haven't even properly named yet, was never designed to save a single animal. And it all started with a telescope. Now, before the telescope, we need to talk about Apollo. Because Apollo proved something that could not be forgotten. That leaving Earth was possible. That the technology to do it could be built, and refined, and built again. That momentum didn't stop when the last Apollo astronaut left the moon in 1972. It carried forward, into the next generation of missions, the next generation of engineers, and eventually into the most ambitious space telescope ever conceived. 1990. NASA launches the Hubble Space Telescope into low Earth orbit. The mission: singular. Look outward. Map the stars. Reach the absolute edge of the observable universe and describe what you find. For that, engineers needed something extraordinary. An algorithm that could identify individual stars by their unique pattern of light. A fingerprinting system for the entire cosmos. They called it the Groth algorithm, built by Princeton physicist Edward Groth in 1986, specifically to help Hubble orient itself among the star fields it would encounter out there. He knew that while stars seem scattered at random, they actually form trillions of unique geometric relationships. He built an algorithm that didn't just look at stars, it triangulated them. It would pick any 3 stars in a field, measure the specific triangle they formed, and then check that triangle fingerprint against a massive celestial catalog. Nobody, and I want to be very clear about this, nobody was thinking about the ocean when he built this. The whale shark, largest fish on Earth, 40 feet long, crosses entire ocean basins. And for most of human history, we had almost no idea where it went. In Madagascar, the whale shark has been known for centuries by the name Marocantana. It means many stars. In 2002, a software programmer named Jason Holmberg went scuba diving in the Red Sea. He had an unexpected encounter with one of these animals. Comes back to the surface completely changed, determined to find a better way to track a creature that had spent centuries evading a reliable count. He calls his friend Zayvon Arzamanian, an astrophysicist from NASA's Goddard Space Flight Center. And somewhere in that conversation, they both have the same thought. At the same moment, the spot pattern on a whale shark skin, that unique constellation of dots running across its back, works exactly like a star field. They took the Groth algorithm. They pointed it at the ocean, and it worked. A telescope built to map the universe was now identifying individual whale sharks by their skin, the same mathematical logic it used to tell one star from another. The system then gets adapted for polar bears, ocean sunfish, eventually dozens of species that had spent centuries evading a reliable count. No conservation budget line in the Hubble proposal. No meeting where someone said, let's build a tool to find the last great fish in the sea. It was cargo nobody packed. And the whale shark was just the first passenger. By the early 2000s, something had shifted. Something fundamental. Scientists had begun to understand that the animals they were trying to protect weren't just subjects of conservation. They were instruments of it. Now, NASA had spent decades developing satellite tracking technology, radio collars, orbital receivers, the infrastructure to ping a signal from a remote animal on the ground to a satellite passing overhead. Originally built to track weather systems, spacecraft telemetry, the cold mathematics of orbital mechanics. Now, strapped to the necks of elephants. Kenya, Amboseli National Park. Conservationists begin using satellite data to track herd movements in real time, not just where the elephants are, but where they're going. And why? Used to find migration corridors, water sources, and conflict zones where herds crossed into human settlements. For the first time, they weren't reacting to the animals. They were anticipating them. But elephants were just the beginning. In Antarctica, we tagged elephant, seals, quietly running a completely different kind of mission. As they dive, sometimes to depths of 2 kilometers, the sensors on their backs are recording water temperature, salinity, ocean current data, in parts of the world where no research vessel can operate year-round. That data eventually becomes part of the UNESCO Global Ocean Observing System, a permanent, living layer of the planet's entire climate monitoring network. The seals weren't conservation subjects, but field scientists. In Tanzania, the same satellite infrastructure takes a harder edge. Space imagery, artificial intelligence, and ground cameras gives rangers the ability to detect human presence in protected reserves with 97% accuracy. In the trial phase alone, 30 poachers were arrested. A technology originally designed to detect objects from orbit. Now watch the tree line for the silhouette of a man with a rifle. What NASA built to navigate the void between planets had become, entirely by accident, the nervous system of the natural world. Now, here is where the story gets really exciting. Because we are not done. The tags that track elephants, hundreds of grams, which means every bird, every bat, every small creature carrying data we desperately need, has been invisible to the network. Until now. NASA's Internet of Animals project, and yes, that is a real thing, I love that name, is developing tracking tags weighing less than 1 gram, lighter than a paperclip, capable of transmitting location, temperature, biological data, from anywhere on the planet to a satellite passing overhead. Think about what that means. A single tagged warbler crossing the Sahara, telling scientists about wind patterns at altitudes no weather balloon reaches. Tagged bats mapping disease vectors before an outbreak spreads. Schools of tagged fish monitoring ocean temperatures across the entire Pacific in real time. The animals wouldn't just be protected by the network. They would become it. The same push toward miniaturization driving Artemis, the need to pack more capability into less weight for deep space, is precisely what makes a sub-gram animal tag possible. We are building tools to survive on the moon. And those tools will help something survive here. That has always been the pattern. That has always been the gift hidden inside every launch. But in 1968, Apollo 8 astronaut Bill Anders pointed his camera back at Earth from the moon and said something that has never stopped being true. We came all this way to explore the moon. And the most important thing we discovered is the Earth. Nobody designed the Groth algorithm to find a whale shark. Nobody strapped a sensor to an elephant seal and said, this will one day map the entire climate. Nobody stood at a launch pad and said, this rocket is going to save something we haven't even thought to protect yet. The accidental ark doesn't announce its cargo. It doesn't know what it's carrying. It just keeps moving, outward, upward, further, and leaves something behind for everything that stays. Artemis has launched. For the first time in 50 years, humans have traveled to the moon and back. And somewhere in the technology that got them there, the next gift is already packed. We just don't know what it is yet.